Thank you. Of Blaine Lawson, and a lot of his work has been well appreciated in physics, especially recently. My acquaintance came actually in 1995 with a particular work that Harvey and Lawson had done, the famous work on calibrated submanifolds. At that time, it was just a few months after maybe what we call the second or third or whatever string revolution. And we were trying to study some aspects of what we call BPS objects in physics, and these are very important objects for physics, and we were trying to solve or understand some classification aspects of them. And somehow we got directed to this paper of 1982, I guess, if I'm not mistaken, the date about 14 years or 13 years before we started this work. And to our surprise, essentially all the classification was there. And it was a very shocking thing for me, because I did not think mathematicians knew about supersymmetry and supergravity, but some of the basic important questions. But some of the basic important questions which we thought intimately related to supersymmetry had already appeared. So this was a bit of a shocking discovery for me, and it's a pleasure to discuss some aspects of those calibrated geometries in the context of string theory, which is what I'm going to focus on today. So I'm going to talk about, from this title you probably would not have guessed this has anything to do with calibrated geometries, not invariants and G2 manifolds, or maybe you would have, I guess, from G2. This is based on various joint works with various people that I have listed here, and some other people which I haven't listed. So I'm not going to be precise about references, if you don't mind. So as Martin discussed in the previous talk, in physics we are very much interested in supersymmetry and supergravity and objects that preserve it.
It's too low, you have to raise it.
Yeah.
Okay.
Yeah.
But we sometimes do the translation, questions in physics and mathematics. Translation is, we typically consider geometries, manifolds which have special holonomy, that means supersymmetric in this context, that preserve supersymmetry, and objects that preserve it correspond in that context to the corresponding calibrated submanifold. So this notion is very natural then from the math viewpoint also, special holonomy and calibrated submanifold associated with them, and these are deeply related to supersymmetry and the objects that preserve it. For example, just to give you an idea about what kinds of questions in physics they relate to, one of the famous predictions about black hole physics made by Becketson and Hawking in the mid-70s was that it carries certain entropy. Black holes in supersymmetric theories get translated to calibrated submanifolds, and you basically are saying, okay, how many of them are there? Entropy means how many of them are there, and you want to count them. Becketson and Hawking made a prediction how many of them there should be in this language, and you could check in some cases that's correct prediction. So questions about black hole entropy, which is a very physical question, gets related to some question in the study of calibrated submanifolds of interesting special holonomy geometry. So it's a very natural and important, as you can see, question for us. So I'll give you a few examples. Again, these go back to the original words. So Calabi-Yau threefolds, if you're interested in the consideration of special holonomy, ST3 holonomy, threefold manifolds is one of the basic examples we study in string theory. For example, if you want to talk about 4 dimensions, from 10 dimensions to 4, there's a 6th dimension missing. And so those, in Martin's talk, as you saw, 10 figured very prominently, and 11 also. So 10 minus 4 is 6, 11 minus 4 is 7. You might naturally think of Calabi-Yau threefolds and G2, and you're not far from where I'm heading. So naturally, Calabi-Yau threefolds and G2 play some role in this kind of phenomena if you want to go down from 11 to 4 dimensions. Namely, you want to think about the space-time as 4-dimensional Minkowski space times something 6 or 7-dimensional, which is special holonomy. Well, what else is there? ST3 and G2. So that's the kind of natural things that you would study in this kind of context, Calabi-Yau threefolds, let's say. ST3 crosses U1, Calabi-Yau times a circle, or G2 would be another example. So we study in the context of Calabi-Yau threefolds, well, holomorphic curves. These will be calibrated with respect to the Kähler form. Or special Lagrangian submanifolds. These are related to the holomorphic n form, in this case the holomorphic 3 form. You could also talk about a combination of these kind of questions. Namely, you can ask, calibrate with respect to the holomorphic, the Kähler class, but allowing them to end, have boundaries. So you look at calibrated submanifolds which have boundaries, with boundaries lie on a special Lagrangian submanifold. So all these questions are natural in this context. Another example are G2 holonomy manifolds. And then in this context, we can have associative or quasi-associative submanifolds. In the context of associated calibrated submanifolds, you're talking about geometries for which the corresponding 3 form for G2 is equal to the volume form, on that, restricted to that submanifold that you're describing. So one basic aim of my talk here is to explain that all these classes, all of the ones I just mentioned, are all related to each other. They're not just examples of the same phenomena, they're intimately related to each other. And I'll try to explain their connections, and their connection to 3 manifold invariants and not invariants in 3 dimensions. So just consider just a simple set of examples. So the geometries I'll describe will not be that fancy, but believe me, it can be made fancy, and we have complicated examples, but in the interest of conveying the idea, I will just basically deal with the simplest examples. So basically my plan is this in this talk. Describe the manifolds first. What kind of geometries we'll be interested in. Review what kind of manifolds we're going to be talking about. And the relation between them. Then we talk about a physical question, some physical set of questions in each case, of like completely unrelated or maybe partially related questions, but not quite the same. And then we find connections between these questions. These connections is what in physics we sometimes call dualities. That questions in one case setup gets related to questions in the other setup, which a priori have nothing to do with each other. Surprising statements of isomorphisms is what we call dualities, and so I'm going to present some examples of those dualities in this context in the context of calibrated submanifolds. Okay, so first, what manifolds we're considering. So we'll basically consider 3 or 4 manifolds, depending on how you want to count. I'll mention why it's 3 or 4. One is, so consider a quadratic cone in 3 complex dimensions. So you have this kind of equation. And we study the deformation of it and its resolution. There are 2 things we can do to get this smoothed out. Either we can deform the equation, or we can blow up small resolution of the singularity. And we will consider both of these things. And another thing we can consider is the G2 manifold. And the G2 manifold that we'll consider will be a cone over S3 cross S3, again, smoothed out in 2 different ways. But in this case, the 2 different ways correspond to basically which S3 you're giving finite size at the tip of the cone. And so whether you count 3 or 4, well, let me count them as 2 different ones, even though they're isomorphic by the exchange of the S3s. Okay, so let's describe the threefold geometries. So we describe a quadratic cone over in C4, which means we are looking at this locus. This, of course, is singular at the origin. And this is what physicists call conifold singularity, and I sometimes refer to it as conifold. You can deform the equation, and you can get an equation like this. Topologically, this cotangent of S3. In fact, the Kähler structure is also compatible. You can admit, for the Ricci flat metric, compatible with that Lagrangian structure on cotangent of S3. In this context, there's a natural special Lagrangian submanifold, which is basically the, if you think about this over the reals, that's the real S3 sitting in the cotangent of S3. And so I'm drawing this picture in terms of the imaginary direction and the real directions. And the imaginary directions is So in this way, this is the S3 part. The boundary of the manifold could be viewed as S3 times S2. The S2 part is contractible, of course. That's just the fact that cotangent direction does not have a non-trivial two-sphere. It contracts to a point, which is the tip of this cone S3. These pictures, I'm assuming, are very familiar. Probably got it from you guys, so doesn't need further explanation. There's another thing you can do, which is called blow-up, or small resolution, which basically means by change of variables you can write this equation like this, and this equation, if you write it in a matrix form, gives you a P1 naturally by looking at the eigenvector, null eigenvector of that matrix, which is parameterized for us a sphere. In other words, the usual blow-up, you consider a geometry which is isomorphic to this except at the origin, whose preimage is a P1, the usual story of blowing up. And what that does is that instead of getting S3 a finite size, you're getting the P1 the finite size at the tip of the cone. So basically these two geometries are related by passing through the singular configuration where either the S3 or S2 gets a finite size. In this context, there's a holomorphic P1 here, and that's the zero section. So the geometry here can be viewed as the total space of the O minus 1 plus O minus 1 bundled over P1, and the holomorphic curve can be viewed as a zero section of that. So here what we just did was, again I summarize here. So we have quadricone resolved or deformed to get a smooth geometry. One in which you have a non-trivial 2 cycle, and the other one which we have a non-trivial 3 cycle. And these could be actually viewed as special Lagrangian cycle there over there, and I can here use it as viewed as a holomorphic in the scalar sense, Lagrangian in the sense of the Kähler form. Lagrangian no, but minimal in the sense of Kähler form. Okay, so those are the two examples in Calabi threefolds. And then I want to talk about the G2 manifold. This example is also a well-known study. In fact, it was the basic example that was studied by Bryant and company and also by some physicists in the context of writing a G2 metric. It's one of the original examples. Involves the following geometry. You study, well, I'm writing here in topological form, some 7-dimensional geometry. Think about 4 complex parameters here with one real equation. If R equal to 0, this looks as a cone over S3 times S3. And if R is positive or negative, you can see it gives you a size either to this S3 or to the other S3. So depending on which way you go, positive or negative. And the boundary of this geometry, the cone is of course S3 times S3, and the radial direction is just how you fill in. And which one you fill in and which one you don't depends on whether R is positive or negative. Okay. But now it should ring a bell in connection with the previous talk. As we heard, the theory was in 11 dimensions, so 11 and 4 makes 7, so G2 could be used as something in the middle there. But Calabi threefolds can't be used in the middle because it's 6, so you need an extra circle, which is that was the last topic that Martin talked in his talk, and the extra circle he went from 11 to 10. So if you view G2 as some kind of a circle fibration over Calabi, maybe then you have a chance of connecting these two ideas. So indeed, geometrically you can think of it that way at least topologically that's correct, namely, you can view this, a natural circle fibration in this geometry, namely, look at the circle action on Z1, Z2, Z3, Z4 given by this action. Namely the last two coordinates. And look at the quotient geometry with that circle action. That will bring us back to the picture we were talking before. Namely, on one side, you just get the S3. This does not act on the S3 part, so the S3 part you see, but the S3 part over here becomes an S2. And this is basically the half vibration of the S3 over the S2. And so you can again go from one geometry to the other, and the one that gets contractible or not, you can just carry over this. So this picture is compatible with an S1 vibration. with this geometry. Now, you might have a little bit of a question in your mind. Metrically, they are not the same. One is SU3 holonomy, the other one G2, so why are we sort of connecting them? It turns out that in the context of superstrings, there's extra degrees of freedom on this, which actually makes the amount of superstring the same as G2. So there's a deformation of a Ricci flat metric on the SU3, which actually is necessary, and that can be viewed as reduction of the G2 manifold on a circle. That structure is a kind of a deformed Ricci flat kind of situation where we have the extra degree of freedom describing this S1, basically. But as you can see, you can describe this geometry and a circle fibration as some kind of system here which looks like effectively Calabi. So far, nothing I hope too complicated as far as the physics goes. But we model out by a Zn now. So the geometry, you remember we have 4 coordinates, Z1, Z2, Z3, Z4. We model out by a Zn, given by an nth root of unity, omega to the n is 1, acting on the last 2 coordinates. This was in the same direction I had taken my circle fibration. So as far as the picture downstairs, nothing changes, because that was the direction that I had modeled out. However, the circle action has a fixed point. In other words, if you look at it over here, the circle action will have a fixed point at the tip of the sphere. Previously it was order 1, but now it's going to be an order n. In other words, the circle fibration degenerates over the special Lagrangian submanifold here, S3, of order n. So that even though on the quotient geometry you don't see anything, there's a data if you want to recover the fibration structure of putting some n units of something there. Namely, you want to remember the fact that there was a circle fibration which degenerated over that submanifold with degree n. Perhaps I should remind how that comes about in the previous student class. Now, even before we model by n, so this point is where the circle action degenerates. As you can see, when you put Z3 and Z4 to 0 over there, that corresponds to the whole free sphere, which is that free sphere which is left over there. So that circle action degenerates over here, but as far as the geometry is okay. But if you want to recover this geometry of as far as the circle fibration, you want to remember that there was something over there degenerating. So that statement is, in the case of the mod n version of it, is that you want to remember that there was an nth order degeneration of that circle. So I put the dashed line here reminding us that there's something going on if you want to recover the fibration structure. Okay, I forgot to emphasize a few things. So this Zn action actually is beautiful because it acts quite differently on both sides. Namely, on one side, actually even the G2 will have a singularity. Would have a Zn singularity. There's a fixed point. But on the other side, it doesn't. So you can go from one side to the other. On one side, you have some degeneration, for which the circle fibration would also have some fixed point. On the other side, you have length space instead. And the circle fibration will not have a singularity, will not degenerate anywhere on this fibration structure. Okay, I think I'm done with the math part. We start our journey. Physical questions. Okay, we have the small resolution of the conifold, which was this geometry. And what we want to do is we want to count holomorphic curves or maps from Riemann surfaces of genus G to this geometry, which are holomorphic maps. Weighted by the pullback of the Kähler class exponentiated, evaluated on the Riemann surface. So there's a Kähler form on this geometry. We pull back and evaluate it on that Riemann surface. That's roughly the area of that Riemann surface. And you want to exponentiate the usual area action or energy functional mathematician, something it's called, that you naturally want to weight these maps with. So you want to sum up such maps weighted by e to the minus the area. Okay, what do I mean by count? Well, for example, if you can take a Riemann surface G, typically it's obvious that it's going to project down to the P1. It's going to multicolor P1 in some funny way. And so you're going to have some families of how it's going to be mapping to the P1, so some marginalized space, and it's not counting. You have to do some marginalized space computation of some characteristic class. The story of this has been well developed by mathematicians. It's called the Gromov-Witten theory, and there's some well-defined characteristic class or extensions thereof that you compute that give rise to what we mean exactly by this counting. So this notion of what's counting is precisely well-defined, mathematically well-defined. Yes?
So you must be saying something poetic here, because any such map certainly is just a map into P1, right?
Yes, correct. But it's like how many coverings of the P1 there are. It's
So
mapped to P1. But we're interested not just we're looking at immersions also, not just embeddings. We're asking about holomorphic maps from Riemann-series of genus G to P1, without, by the way, fixing the complex structure of the genus G curve. So you're also that family of which complex structure you choose and all that. So it's a complicated problem. But counting, it's not a trivial problem by any means.
But X, in fact, is not playing any role here because it just winds up in the zero.
Exactly. It becomes, the bottom line becomes a story about the P1 by itself. In this simple example, it doesn't play a tremendous role except to defining what characteristic class you want. So if you did this P1 inside, not a Calabi just by itself, you'd get a different characteristic class. So precisely what you're computing in that family depends on the fact that this is coming from a Calabi. Okay, you want to compute this? Well, there's a natural thing to do first of all, because you can also grade this with respect to the genus of this Riemann surface. So you want to also count on which genus you're computing. So it's natural to put all this computation up together. So in physics, we always usually add up all these different objects with some kind of coupling constant, which in this case is called a string coupling constant. So we put a factor of lambda to the power of the Euler characteristic, 2g minus 2, or minus the Euler characteristic, and you weigh it with the corresponding parameter, lambda to 2g minus 2, the answer that you would have gotten by summing over all genus G curves wrapping around P1. The area of the basic P1 I'm calling T. You can have multi-wrapping, so this is going to be a function of e to the minus t. Depending on how many times wrapping you get e to the minus nt. So we're going to have some function of e to the minus t, which depends on which genus you're interested in, by doing this counting. And you sum up over all genera with some weighting. And this is going to be giving us a function. I guess I've missed here putting a t parameter there. A lambda parameter. So it's a function of t and lambda, which depends on the Kähler class of the P1 and the string coupling constant, which tells you which genus contributes in what way. Is that clear? Well, that part I hope is clear. This part might look, where did I get the last formula here? This last formula is doing that computation. In this case, it can be done. As was pointed out, the geometry is not that complicated after all, it's just a P1. So we can do this multi-covering and all that. So this actually has been computed both from a mathematical viewpoint by Fabian and Daripande, and from a physical viewpoint, and we of course agree on the result, hopefully. And the result is this. Namely, you look at this and expand in powers of lambda, you notice that the leading power is a 1 over lambda squared here, as lambda goes to 0, which means that the genus 0 contribution is the leading singularity as lambda goes to 0. And if you look at the lambda equal to 0 term there, you get e to the minus nt over n cubed, which means that you basically have a map from P1 to P1. The basic map is just 1, is e to the minus t, that's good. But the multi-cover of them is getting counted by 1 over n cubed. The characteristic class computation you're doing gives you a factor of 1 over n cubed for n times multi-covering of the P1 by P1. Similarly, if you expand this in terms of lambda, you get some Bernoulli numbers in terms of the expansions of sign, which come from doing some characteristic class computation of the marginalized space of these maps to P1, and that collects beautifully in terms of the sign function, which is amazing. But anyhow, it has been done, and I agree. That's the answer. So this is the physical question and the physical and mathematical answer at the same time. Next question. The same kind of question on the deformed manifold, which is the geometry which is cotangent of S3. Now here there's a special Lagrangian submanifold wrapping S3, which we can take it to be on S3. We do the same kind of question now, but we want to do holomorphic curves. Here we have this extra thing we can do, namely we can allow for the holomorphic curve to have boundaries, for the Riemann surface to have boundaries, ending on the Lagrangian submanifold. So that's what we do. We say, consider genus G Riemann surfaces without fixing the complex structure, with H boundaries, mapping to this geometry, such that the boundary of the Riemann surface lies on S3. You look at holomorphic curves like this. And then, once you look at these holomorphic curves, you count them. So for every genus G with some hole, you get some number, depending on number meaning some rational number. You get some kind of characteristic class computation as before, some kind of computation. And you weigh it with, again, the string coupling constant, lambda to the 2G minus 2. And then you also want to count how many holes it came from. So you put an extra factor here, n to the power of number of holes. Said differently, this n can also be viewed as multiplicity of the Lagrangian submanifold on S3, how many times you put it. So if you think about a sheet or something wrapping the S3, you can put n copies of it. And when you are looking at the Riemann surface, you can ask on which one of those S3s a particular hole ends on. And there are n choices, which one you want to choose. So for each hole, you get a degeneracy factor of n. So the multiplicity n of the special Lagrangian in that language means weighing each hole with an integer n to the power of the number of holes we get because we have h holes. Any questions so far? The question is, can this be done? Well, first of all, we have to make note of the following fact. There are no honest holomorphic maps. So you might have wondered, why am I talking about cotangent on S3? What kind of holomorphic maps are there which end on S3? There's none, really. But there is something which is a degenerate limit of the Riemann surface, namely, there are, in fact. Since we are not fixing the genus G curve, we are looking at families of the whole possible genus G curves with H boundaries. You get, as we approach the boundary of the marginalized space of genus G with H holes, you get almost holomorphic maps. So in the degenerate limit, you get contributions from the boundary of the marginalized space of genus G curves with H boundaries. And they will look like infinitely thin Riemann surfaces with holes. So you get some degenerate Riemann surface, which are would-be holomorphic curves with boundaries. These look like Feynman diagrams of some particles moving on S3. You get graphs on S3 with some ribbon graphs. You get some ribbon graph on S3, which would be the degenerate limit of that Riemann surface. And in fact, this has been interpreted long ago, 10 years ago or so, by Witten as precisely being equivalent to the field theory you would write down for Chern-Simon gauge theory on S3. So this counting problem of the holomorphic curves ending on S3 is just the good old kind of, in physics terminology at least, the good old Chern-Simon theory on S3, where the dictionary is that you're talking about the UN gauge symmetry, UN being n being the degeneracy on this S3, how many Lagrangian, special Lagrangian submanifolds you have. Yeah, so these degenerate limits in the algebraic geometry people also talk about. So you talk about families of all maps. You go beyond the holomorphic category. You study all maps, and you localize in that context to near holomorphic maps by some configuration. So in that bigger space, there's a sense in which these end up being holomorphic in the same way. So I think these are called bubbling type configurations, if I'm not mistaken, in algebraic geometry, but basically degenerate limits of holomorphic maps. Yes, exactly. They have genus G with H holes.
No, but they satisfy equations.
You have to sum over all of them. So in other words, you have this S. No. You have to sum, just like it's like in Feynman diagrams, you sum over all paths. So you have to sum over all graphs. And that's precisely what this genus G map should be. You have a marginalized problem and all that. But that marginalized problem is, so if you appreciate what math problem that is, then you know a Feynman rule for that theory at least. That is the Feynman rule for that theory, precisely the sum rules of how you sum over these graphs. So you can get it from that degeneration limit if you wish.
So they're thinking about that, how do you sum over all graphs?
You have to, there's a marginalized problem. It's just like how, even in the previous problem, we summed over all maps from P1 to P1, or genus G. This is a finite dimension. Oh, this, is that what you're asking? Yeah, so there's a S3, there's a finite dimension that points to points, but you have to sum over all possible paths, which is in the boundary of the marginalized space. You do have that degeneration. There's a length, the geodesic. So if you have annulus, for example. No, not geodesic path. No, I'm not saying it very clear. There's a marginalized problem on the Riemann surface itself. So if you take the annulus, there's a marginalized for the annulus. There's an infinite parameter there. Okay, so there's an infinite length, so that means corresponding to which length you're choosing. But you have to consider all possible paths, lengths that you're, so you choose all possible lengths and all possible maps of that driven graph to S3. So it looks like an infinite dimensional problem in that sense, and it is. It is, you have to sum over all these paths. It is a field theory. But of course, it's not as complicated as I'm saying, because sum over each pairs of points of these ribbon graphs, of these, for example, ribbons that you consider, just gives you the Green's function. So it's not a complicated object, basically. That sum is easy to do over all possible paths. That's just a Feynman description of how you get the Laplacian, the Green's function for, let's say, Laplacian of the corresponding operator in this context. So doing that sum is easy. That's just since it's quadratic, you can invert it, and that sum over paths becomes just the Green's function. So some sub-pieces of this are done. In fact, this object itself has this like in mathematics for a given ribbon graph, and these are called the G, H invariants of three manifolds defined by Witten, which is basically this. And for example, Taubes and others study properties of how you precisely define exactly these invariants for each manifold, not just S3, for any free manifold. So for a genus G with H, you can get these ribbon graphs and get invariants for three manifolds. It's well studied also mathematically. But another problem mathematician studies this one. And the path integral, you have to still, this is the Feynman diagram for the path integral. So you have to do just the usual Feynman diagram. There's no, there's no better way than the Feynman diagram itself in that context. So I didn't spell the dictionary property yet. So the string coupling, in this case that I just defined before, for it turns out to be related to the parameters of the Chern-Simon theory, K, level of Chern-Simon, in that way, and the N is the rank of the gauge group. So in other words, this problem turns out to be equivalent to a field theory, which can be written like this. What this means is the following. We have a UN connection on S3, and you want to sum up over all the gauge inequivalent connections on S3, UN connections, weighted with the exponential of ik times the Chern-Simon action. The Chern-Simon term, of course, is defined up to shifts by integer, which is why this k, or shifts appropriate half integer, whatever, which is k is integer. So k has to be integer and it will only appear as e to the I, otherwise the weight is not well defined. So this thing is gauge invariant, this weight. So you can have a k and an n. You sum over this, you get something which is going to be a function of k and n. And that function is equivalent to this funny degenerate limit of these Riemann surfaces I was talking about. This is difficult to compute term by term, but you can do these Feynman diagrams I just told you. But there is a trick to compute it directly and exactly to all orders, summing up all of those diagrams. This has to do with people who study three manifold invariants and the relation that this has with some Hopf algebra, quantum algebras. And this relates to, in physics, what we study as two-dimensional rational conformal field theories. It's all study Berlin, the algebra, and all that. So this whole story gets related to yet another branch of math, the study of those objects, quantum affine algebras and their representations, and aspects of that end up giving the answer here. To be precise, the answer here can actually be written in that language. So you have various characters for these representations, which are modular objects, and you can talk about how they transform under tau goes to -1 over tau, and you get this famous S matrix. And the answer for this turns out to be S00. That whole sum over S3, that complicated sum, can be reduced to a statement about representation theory of affine Kac-Moody algebras and their characters and how they transform under tau goes to -1 over tau. A completely unrelated subject yet. which I didn't want to go into too much, but yes, it's connected to this. And the answer for this sum turns out to be related to studying how the affine characters transform on the marginal transformation, and a particular element in that matrix gives you this answer for S3. Okay, next, G2. On G2, what we're going to study? Well, in the G2, it's natural to study calibrated geometries. In that case, you just have S3s, or 3 cycles in general. So if you have some manifold like this modded inversion of the geometry I talked about, you can talk about 3 manifolds drafted to this geometry, again, which are associative. And you can think of them, if you wish, as related to the circle fibration over the corresponding genus G curve you were talking about in the context of Calabi-Yau. So this lifts up, if you take this genus G curve and lift it up to the nth degree under the circle fibration, the total space over this will be some kind of 3 cycle, which is natural to sum over. And with some appropriate weights for this, which has not been defined mathematically yet, so the analog of Gromov-Witten theory is not defined yet, but it should be existent. There's some analog there. Should give you what would be the analog of the object you would want to compute, which is not directly computed yet. This. Namely, the analog of what these geometries are and how you sum it up. Since it's not developed well. Okay, so I'm just saying that for every genus G curve down there on a Calabi-Yau, you have a total space lifts up. There was 3 cycle over it. Yeah, so some kind of contribution from that you want to compute. Precisely how you sum it up and so on has not been defined mathematically, but it should be an intrinsic theory, not just the lifting up from some lower one. It should be an intrinsic theory of how you sum up these objects, which has not been defined mathematically. In certain cases in physics directly you can compute them, but there's no general theory in physics either. Right. A priori, the analog Gromov-Witten theory for that has not been developed, but we know from other physics arguments they should exist. So there is a good question there for mathematicians to develop. Statements of equivalences. I talked about the counting of holomorphic curves and the resolution of conic geometry. Remember that S2, finite S2, which was nice holomorphic curves, wrapping over this with genus G and so on. On the other talk, I talked about this partition function of these degenerate Chern-Simon kind of computation. The statement is that they are equal to some appropriate dictionary. Namely, they both had that genus counting parameter, which I call the string coupling constant. But one of them had n weighing how many holes there were around, and the other one had t, which was the Kähler parameter of the P1 in the target. So you all have to find the relation between this t and n, and the relation is not that difficult, it's just n lambda. So the statement is that if you compute this and just plug in this, you get the answer on the other side, which was related to this Chern-Simon theory. And the corresponding object in the G2 context turns out to be related by a physical reasoning, but not by direct computation, to a derivative of this function with respect to t times n. So the whole 3 objects would be related in that context. Since there is no direct computation of this, I cannot check this, but this part can be, of course, checked. Okay, I said these are equivalences. It looks like black magic. What's the motivation for these statements? The motivation comes from de Hooft, actually, a long time ago, in 1970, I guess 2 or 3 or something like that. He studied the large n limit of field theories associated to UN gauge groups. And he noticed that they organize themselves into some kind of a ribbon graph Riemann surface structure, and he said, well, it'd be nice if the holes disappear, and you get a smooth Riemann surface. So he conjectured that somehow those holes get filled, and you get a closed Riemann surface out of those Riemann surfaces which has holes, with some dictionary, which he didn't figure out, and it was too complicated, but he just postulated there might be some math like that. In physics, the corresponding computation on the S3 side we call the gauge theory, because after all it was a Chern-Simon gauge theory, we had connection and all that. On the other side we call it gravity. namely this maps holomorphic maps to P1. After all, it's just Riemann strings moving around closed Riemann surfaces. We call it gravity. So it's a kind of an equivalence statement of what we're talking about, the equivalence of some gravity computation with some gauge computation. Sorry? Right. No, this is topological gravity. Yes, it is. Well, everything, here's topological gauge theory too. You can put the things there. So that's the kind of motivation you might have expected that it could be there. In fact, you can actually make it more precise, namely, you can look at this genus G map that we had to P1. Think about this P1, it's going to shrink. So now let's go through this transition we have. We have P1 shrinking and S3 growing. Once P1 shrinks, you don't have any more holomorphic maps. So what happens if you continue computing this kind of objects in that limit? Well, now you have a way for them to develop holes to end on Lagrangian. So out of that, S2 grows an S3, but which is special Lagrangian. Holomorphic curve can only end on it, it cannot wrap around it. So it's natural that this problem might be related to this kind of problem, even mathematically from that viewpoint, that this problem fits deform to that problem. But in that case, what should happen is that for a given genus G, you should get the answer for all with the same genus but arbitrary number of holes. And that's in fact true. Namely, it's more, if you follow what this dictionary means, it's order by order in this particular genus expansion. Namely, if you get a fixed genus on the one side, on the other side it develops arbitrary number of holes and you're summing up over all number of holes. This leads, yes? Okay, so from mathematical viewpoint and even physical it might look mysterious, but in fact we have understood it recently from physics viewpoint how this works. The idea is actually very, very simple. What happens is you study a field theory on this Riemann surface which has to do with this propagation of P1. Precisely when the P1 shrinks, it develops two kinds of phases, like a water and gas phase or something. And these two phases you have to sum over. So the Riemann surface has two different phases, and the phases in which it's one type becomes the hole on the other side. So this description in terms of the two-phase system becomes holes versus non-holes. But then you have to explain what happens when the other phase is non-trivial topology, not just the disk. You can find that they are actually zero. So the only topology that contributes for the other phase is this topology, and then you get the sum on the other side. So from physics viewpoint, we have an understanding of how this works actually now. But anyhow, just to give you some idea, this leads to highly non-trivial predictions. This equivalence between a UN gauge theory and gravity is a very non-trivial statement. And just to give you one indication, or just to give you one particular aspect of that statement. So among the prediction it makes is the log of the volume of the UN gauge group computes the Euler characteristic of marginal space of genus G curves. You can check this formula. The left-hand side is computed, and also the right-hand side is computed by Zagier and Harrer and Penn and so on. That's much harder, yes. But they are equal, and you can just look at the tables and you can check it works. This particular statement of this duality. So on this side is the gauge theory statement, UN. On this side is the Riemann surface story, marginal space of genus G curves. Completely bizarre statements, but these are the kind of predictions. That's a map. You can just check this is correct or not. The consequence, both sides of it make sense. You can check it is true. The explanation is the one I said. Or you can find another explanation. This is at least an explanation. You're welcome to try it. In fact, it's not actually, I shouldn't say, I'm not making this in a funny remark. In fact, Zagier and Harrer and also Penner, if you remember, they were actually using a matrix integral. Matrix to us is a gauge theory. So they had a gauge system in this language. So they had a gauge system which computed characteristic classes. And they understood how it works, namely the cell decomposition of the marginalized space got related to the matrix graphs that I was talking about, this Rubin graph. So in that case, they understood this map, how it works. This, if you wish, is a slightly generalization of that same general idea. So that idea may not be that difficult, so it may actually be possible to push these two theorems in math even, understanding similar to extension of what, for example, Zagier, Harrer, and Tenner were doing. Or also Concierge in his integrals. And the relation to counting associated cycles on G2, well, let me just make one remark about that. On this side where we talked about where you had holomorphic curves ending on S3, there was a circle fibration. So this genus G, which ends on S3, if you lift it up to empty, it becomes a closed Riemann surface. Closed three manifold. Because remember, the S3 was precisely where the circle fibration degenerates. So the total space of this is nice and closed. It's just a push down that looks like open Riemann surfaces. So the study of closed Riemann surfaces with boundaries is naturally pushed up one step up to a nice object without boundaries, where that circle fibration exists in that sense. So that circle fibration is precisely crucial, as was discussed in the previous talk about going from 11 to 10. At 10 you got string theory, and pushing it up to get M theory. These three-dimensional object is what Martin talked about in that context as M2 branes. These would play the role of associative manifold in that case. Again, the fact that we don't have a good theory of that, which Martin mentioned, is the fact that we don't have a direct computation on that associative submanifold summed over G2. That exemplifies the statement Martin made, that we don't have a good theory of these a priori. But in reduction to a circle, reduction over a circle, we do have a good theory. This is the Gromov-Witten type theory and so on. Even the math of it is well defined, and we can compute things, and we can then push it up. That's an example of how this perturbative picture can be lifted up in M-theory context to statements about these geometries. And on the gravity side, again, these you have some half-type vibration and order n vibration version of half. And so anyhow, you can lift it also that side and get similar prediction. Okay, now I want to actually extend this to include not invariants. So those who are familiar with the study of topological invariants for three manifolds, or even those who have studied it so much, they might know that there's a connection between defining these three manifold invariants and not invariants. After all, the surgery naturally connects them. So studying one and the other is kind of related, so it's not unnatural to that. Then if these are corresponding to three manifold invariants, to ask whether we can compute not invariants in this context. Well, we have a geometry which is a cotangent of S3. How do we get a knot? Well, we just take a knot in S3. Some link or knot or something, take it on S3. But to that, there is a canonical associated Lagrangian submanifold. Because cotangent of S3 is symplectic, so if I choose this, you can have this conormal construction, you can get the natural Lagrangian submanifold. I call it L sub gamma, which intersects S3 over that knot. It's canonical construction. So in the picture I was drawing here, if I think about these S3s, right. Exactly. The two-plane bond along the knot defined by the symplectic structure and the cotangent of S3. So L sub gamma will be non-compact. It goes off to infinity, and then you have this S3 over here, and they intersect over gamma there. Now, then, in this context, what are we supposed to do? Well, holomorphic curves. Again, holomorphic curves with boundaries. Boundaries are of two types now. There could be either ending up on S3 or on L sub gamma. So there's two different kinds of boundaries you can have now. So you look at Lagrangian submanifold, which can end on either one. In other words, you get Riemann surfaces like this would have boundaries on L sub gamma or on S3, and you now sum up these guys. Again, you end up with degenerate ribbon graph type pictures, which turn out in the Chern assignment to be computing these not invariants for that gamma. So you get the expectation value of these holonomies. So if you take U to be holonomy along this gamma for this UN connection, evaluated in some representation R, weigh the path integral with that weight, that gives you the not invariant for not gamma in that representation R, and these kind of computation get related to these kind of sums in this degenerate limit. Well, what should we expect in this picture, in this duality? Sorry? No, again not. Again, they're just degenerate. So you're on this side, there's some degenerate curve which gives you the Chern-Simon theory of these knots, but then there's this picture that this shrinks and then grows on the other side. But this non-compacting cannot disappear. It stays there. So you end up getting a Lagrangian submanifold now on this S2 side, on the resolution side. Now you can ask continue the same question. What about the holomorphic curves which end on this Lagrangian submanifold? Here you have two types, but here you only have one type. Here you only had degenerate ones, but now here you're going to get nice ones. So the degenerate limits of these Lagrangian of these holomorphic curves now become ordinary, nice, good old holomorphic curves with boundaries ending on f sub gamma. For example, if you study for the unknot, for the trivial knot, the Lagrangian submanifold will project down to a circle on the P1, and you have this non-compact 2-1 over that circle, which is the Lagrangian submanifold. For example, you have a holomorphic disk like this. And you can have a genus G version of it, which is ending on like that, and that perfectly smooth, nice holomorphic curve with boundary. This actually translates the problem of knot invariance on their computation to an integer expansion which was unpredicted. So a very surprising integral structure appears, which basically means now counting how many genus G's there are with some boundaries on this dual picture, which has nothing a priori to do with the knot. In other words, for every knot type, you get a canonical Lagrangian submanifold on the resolution side and ask how many curves of a given genus with this, count them. This gives you a knot invariant. It's a strange way of getting a knot invariant, but it captures all the information for Humphrey polynomials in particular. So there's integral questions. So the algebraic geometric prediction of integral computation of the knot invariance exists. It should be defined mathematically precisely, but we have no doubt exists. For example, we have computed on both sides a certain number of non-trivial examples like torus knots and so forth, and things work. And also the fact that this Lagrangian submanifold exists on the dual side has actually been established mathematically by Tau, so you can actually construct this Lagrangian submanifold to a given knot type. So there's now a question. Compute the Gromov-Witten invariance in that context of holomorphic curves with boundaries, and you should end up with a knot invariance for the corresponding curve on the other side. Okay, that's a very good question. It turns out that indeed the Gromov-Witten theory can also be described by some new invariance that Kumar and I studied, which is integer. So it turns out that the Gromov-Witten invariance can always be written in this form. So if you have, for example, some Kähler parameters, let's just take one of them, just the one I have, it can always be written in this form. So in other words, there's a two-integer family of invariants. These integer now, really. So all the rationality and so forth of Gromov-Witten is captured by the fact that sign has these Bernoulli numbers. That's all. Sorry? It's not very legible, I see. So let me write it a bit more. Where n is bigger than 0, s is bigger than 0. We can also take the limit where it's actually 0, and s is bigger than or equal to 0. So, and d is integer, positive or negative. This is a physics prediction, yes. Yes, yes. It has been checked in a number of examples by mathematicians as well. Yes, it's not a theorem yet, no. But in all cases, we know it has been checked and there's a physics argument for it. So this translates in a similar context, an integer expansion, just basically counting these more primitive invariants. You don't have to deal with the rest of it. This is the basic story. And roughly speaking, the difference between them is the difference that was related to the question asked between immersions and embeddings. So in this count, you're roughly counting curves inside the manifold, not maps. This boring multi-cover and all that you don't want to interested. You're interested in counting curves inside the manifold. This is what you count. And those are integer. But how you count them is a non-trivial story. It has to actually, it's not just it's not precisely just the holomorphic curves. You study holomorphic curves with a line by line. That total study, you're studying that object and you count those objects as objects inside that manifold. Anyhow, there's a long story to that, but I don't want to go too much into that. Anyhow, there are some integer expansions there. Finally, let's see, I think I missed some part of my transparency. Yeah, okay. What does this have to do with G2? G2 suddenly disappeared from my discussion. G2 gives a conceptual picture of how this duality works. Namely, on the G2 side, we compute something on one or the other side, and we just take a continuation of the analytic parameter, that R I wrote. R that I wrote goes from 0 from one side to the other, that volume. Now, that's a bit singular at R equal to 0, right? So it's not, so there's no notion of analytic continuation in R. That's a real parameter. The radius of that is 3. In physics, it turns out that R gets complexified. So you get a complex parameter, not just a real parameter, and you get a singularity at R equal to 0, which is point singularity, not a whole circle. So in other words, you have the notion of analytic continuation from one side to the other. So what this statement ends up saying is, you're computing something on one side and doing analytic continuation to get the answer on the other side. Big deal. Okay? From this upper viewpoint, it's kind of trivial. So once you develop this associative submanifold discussion, it just trickles down to this statement that I'm making as a trivial consequence. So the G2 explains, in a sense, the explanation of this statement would be a G2 in the physics, which is M-theory description. Again, going from 10 to 11 dimension. That explanation lifts up to this question here. Again, in this case, for example, if you have knots and all that, what you're studying, yeah, this is worrying on the continuation of something and say formula.
So the other side that you're using from Cumrun?
Right, the analog would be the M2 branes and the associative submanifolds they associate with and so on. And over here, again, these all lift up to some G2 manifolds where you just have circle fibration vanishing on some order here and also on here. That's all. So the circle fibration will have more degenerate points. Whenever you want to put Lagrangian submanifolds down here, think of it as circle fibration which is degenerate. That's all. And so on G2, you go from one to the other, and that will give you a map from one to the other. Where the circle fibration is degenerate here, but when you go to the other side, the circle fibration is degenerate only over the knot part, but not the other part. That's all. So I think I'm exactly on time, so I'll stop. P1 side, which is S3 mod Zn fibration over P1, that N has to do with the fact that the fundamental group of S3 mod Zn is N. And you're considering associative submanifolds on S3 mod Zn, but with a flat connection. There are N choices of flat connections. That factor of N is related to that fact.
All this geometry is essentially a single one parameter manifold.
Yes.
What happens to the other manifolds?
Yes, well, I have to be honest, the families that would be interesting from this one would be the one which is associative submanifold, so there are not that many. at least I don't know, maybe you can explain to me. They're mostly the ones which have 4 cycles, co-associative stuff. Those would not enter as interesting questions here. In fact, they don't have anything like this because you don't have any M2 brane. It's 3-dimensional, so there's nothing in that sense 4-dimensional. But there would be another, I should say that there should be an analogous co-associative version of this, namely sum over co-associative things, which is not the story I'm talking about here, but yes, they should exist. For this, I should add that these have been extended to non-trivial topology, so I want to actually mention some examples. I talked about the P1 inside the Calabia, that's kind of boring. But you can also have a P2 inside the Calabia and curves in P2. That's not boring. That, as we know, is very non-trivial. That can be done, and those things can be related to knot invariants and hop things and all that. So the connection between topological invariants, counting grown with invariants on one side, Chern-Simon like knot invariants on the other side are now one subject in the sense they all mix up as far as the physics goes at least.